Naumann is going to talk about the role of p-divisible groups.
Welcome everybody. Thank you very much for having me here. Thanks for reminding me to put the mic. Is that okay? Yeah, okay, I hear myself. Okay, thanks again for having me here. As a reporter on recently released work of Jacob Lurie, so the appropriate title is Report on Parts of Jacob Lurie's work Elliptic homology 2. Which has been available on his homepage starting this January, I think. And even with this is a very reduced ambition here. I will only report on parts of the second part. So this is nowhere being close of being a full account of Jacob's work on these things. So I reiterate an announcement which probably most of you have seen on the topology service. So more on this at Oberwolfach. There's some upcoming Arbeitsgemeinschaft at the Math Institute at Oberwolfach, Arbeitsgemeinschaft. This is next year, March 31st through April 6th. 2019. And the organizers are Paul Gors, Jacob Lurie, and Thomas Nikolaus. So there is an entire week dedicated to this, to these results, to this mathematics. And if you're interested, I guess you just want to sign up and go there. And I like to try to report on the following result. Theorem 0.08 of that work. For the ease of reference, I use the labels from the paper so you can see what I'm talking about. So assume P is a prime. R0 is a Noetherian FP algebra. And G0 over R0 is a p-divisible group, one-dimensional. Such that the following assumptions are satisfied. So there is a fairly mild finiteness assumption on R0, which is even removed in the main body of the work, but I'm sticking with that for the simplicity of exposition, which is that it's F finite, so that means the absolute Frobenius of R0. So the map which sends x to the p is finite. So it makes R0 a finite module over itself. And the more subtle condition is that G0 over R0 be non-stationary. And I will explain that in maybe 5 to 10 minutes. It's a little technical, but it's satisfied in many cases of interest. Then there are the following two statements at least. First, there is a universal deformation. Say G over R G0 CL of G0 over R0. So this is purely a statement about commutative algebra, or at least classical things. This p-divisible group admits a universal deformation over some deformation ring, which is labeled R G0 because it depends on G0. and it's labeled CL for classical. So there is a universal deformation, and I think actually, truth told, I didn't completely investigate, but I think even that classical statement is already more general than things that were available previously in the literature. But of course, the interest here is from the second statement that this lifts to homotopy theory as follows. There is a weakly two-periodic E infinity ring. So C-alg stands for commutative algebras, and that is a notion equivalent to E infinity rings, such that the homotopy of E is concentrated in even degrees. Then there is a relation with this universal deformation, namely some specific ring map, which I will explain, from the classical deformation ring to pi naught of this E I'm trying to explain is an isomorphism. And to pin that down, at least as a cohomology theory now, that it is evidently complex orientable, you can just ask what is the formal group attached to it. So E naught of Cp infinity, that's a formal group, and that is given by the identity component of the universal deformation, which, oh, I gave it a name, fantastic. So G naught, the identity component of G. It wasn't very easy when thinking about this 2-hour presentation which things to say at which point. I'm well aware that probably some of these terms aren't fully clear to all the participants. My only aim in the first hour, and probably the first hour is not even going to be sufficient for that, is to just give precise definitions for all these things, but I thought it would be more instructive to have them seen stated once, even without maybe completely understanding it. So at least, okay, this is the main theorem, and here are a couple of remarks to maybe think about this. The first one is that this validates all the results from Mark and Tyler's work on topological automorphic forms. So this is Behrens-Lawson topological automorphic forms. This is an AMS monograph. As I said, this result of Jacobs had been announced a very long time ago, and then of course people go try to just see what you can do with it. And so in this book, basically Mark and Tyler show that they can use suitable Shimura varieties to make these situations happen. So to apply the theorem. And back then, this was of course only announced and not proved, and now it's proved. As one of the main interests in all of this construction, at least according to Jacobs' introduction, was a better understanding of elliptic homology. Let me briefly say what this does for you with respect to topological modular forms. This result by itself gives the spectrum of periodic topological modular forms completed at any one prime you want, but not anymore, but not integral TMF, and also not any more global versions towards the connective cover, nor a modular interpretation. All of this is available in Jacobs' work. I'm just trying to make clear the limitations of my exposition. I mean, this is in part 1 of elliptic homology, the modular interpretation, and also to need the integral construction, you just need to know what a spectral elliptic curve is, and I will not even define this. I just had to cut that from the presentation. But if you want to see more of this, you have to come to this Oberwolfach event, which I advertised previously. So I'll have to Do you share the fun?
The overhead projector came on and then turned off.
Oh, sorry. Thanks. Okay, thanks. I have to say what this non-constant means, even though at first sight it looks a little technical. But then actually, at least for the rest of my contribution here, it will always be automatically satisfied. But we'll say it anyways. So this p-divisible group is non-constant. Means the following. Assume.
Supposed to be non-stationary, or?
Oh yeah, absolutely. Thanks. I auto-confused myself. There is no non-constant, non-stationary. If for any point in the spectrum of R naught and for any non-zero derivation from R naught into the residue field at X, whenever you give you this situation, you can cook up two ring maps, which are actually tangent vectors to the spectrum of R naught at the point X. These are the following two ring maps to the dual numbers over the residue field. So the one is the trivial one, say alpha naught, which maps F to just F plus 0 times epsilon. This is a small abuse of notation. I use F for an arbitrary element in R naught as well as for its image in the residue field. So this is just the map and then include it into the dual numbers by putting the epsilon component to 0, or you can put the derivation here. So this is, of course, let me finish the statement. Whenever you have such a situation, then you can push forward the p-divisible group by any two of them to the ring of dual numbers, and the requirement is that you, so the one ring map is alpha naught and the other is, who knows, alpha, be not isomorphic to alpha g naught. Yeah. I felt I should bring that up in its full technicality at some point, but what that really is saying is that the classifying map, if you look at the classifying map of G naught to the stack, moduli stack of p-divisible groups, then this induces at any point here a map on cotangent spaces, which are these derivations are the algebraic cotangent space, and those are supposed to be injective. Dually, that means the map on tangent spaces should be surjective, and this is a classical versality as in Artin's deformation theory in the 16th. So this is a very familiar condition, but well, okay, there it is. Here's an example which will actually be satisfied in all the applications I will talk about if just R naught is semi-perfect, which just means its absolute Frobenius is surjective. For example, it's a perfect field. Then, of course, every derivation automatically is 0 because the derivation vanishes on pth powers, and then the condition is vacuously satisfied. So that means every p-divisible group is non-stationary. So there are certainly plenty of examples, even though, yeah, okay. So here's one key example, both to this theorem and to the general theory we've actually seen in the last hour. So if you take R naught equal kappa, a perfect field, necessarily of characteristic P, because I'm constantly assuming it's an FP algebra, and you take G naught over kappa to be a P connected, and the datum of a connected p-divisible group over a field, positive characteristic P, is equivalent to the datum of its identity component. This is true even for higher dimensional ones, but anyway, I'm assuming it's one dimensional. So the datum of this p-divisible group is equivalent to the datum of this thing, and this can be any one-dimensional formal group of finite height. all the formal groups we've seen come up previously when talking in the last hour talking about Morava E theory, were such formal groups of finite height, and those are the identity components of uniquely determined connected p-divisible groups. So this is why all this of the last hour is subsumed in the setup of this theorem 008. Just not the result. The result as well, of course. Then if you make this choice in theorem 008, then the spectrum promised over there is a Lubin-Tate theory. Yeah. And that was called Morava E theory last hour, but I will not try to. I get confused if I try to adopt the notation here. So E is Lubin-Tate theory, and the construction given here. So this is an existence statement. There is an E infinity ring spectrum with all kinds of nice properties, and the existence proof given by Jacob is completely independent of the first account we have of this result, which was mentioned last hour. So this is independent of Hopkins-Miller. Okay, there is a new proof for the existence of Lubin-Tate theory here, and it is in fact a key step in the proof of the general result. Key step in the proof of 008. So while it is a new and independent proof of the existence of Lubin-Tate theory and its basic properties, it's also a key step in the generalization articulated in this theorem 008. And it's in fact the only thing I will talk about in the rest of my time. I will not go anywhere beyond the case in this theorem where R0 is a perfect field.
That would also give the uniqueness?
Yeah, it depends, uniqueness subject to what? I mean, it is not, yeah. I can tell you afterwards, okay? Okay, here's an outline of this proof. So this is going to be a huge number of hardly defined terms, and the challenge in the rest of this first hour will be to at least provide all the exact definitions, but I hope one can get an idea. So okay, the starting point here is this given p-divisible group G0 over R0, and you can first do some classical commutative algebra, and I try to sneak in the notation from Jacob's work so you get used to it. This is called C-alg-hard. This is the category of discrete commutative rings. And you can try to ask for the most general deformation of the given p-divisible group inside that category. And there is one, it's even announced, it's part one of the theorem. There is a universal deformation, G over R, G not classical. And this then comes with a canonical surjection down to R0. But you can, I mean, this is the first major contribution of this work. It's a fantastic proof of concept. You can make sense of all of the players involved here in the more general setting of connective E-infinity ring spectra. This is called C-alg connective. Say what a p-divisible group is, what a formal group is, and what a deformation is. And then Jacob proves that there is a universal deformation in this more general setting, RG not UN. This comes from universal unoriented deformation. In a minute there will also be oriented deformation, so this is this funny notation. And then this bears the exactly same resemblance to the classical deformation ring that the classical deformation bears to the initial ring we started, namely this identifies with pi naught of the unoriented deformation ring. So this is the idea that a general connective E-infinity ring is a nilpotent thickening of its pi naught. So you extend the modular problem and everything from discrete rings to connective E-infinity rings, you get a universal deformation ring, and then necessarily, if this works out, its pi naught has to be the classical deformation ring. And of course that can't be the ring spectrum E announced there, because it's still connective. So to go further, one needs to revisit this foundational contribution of Quillen's, who observed that certain ring spectra come with naturally attached formal groups to them, and those are, say, E. This is a complex periodic ring. It roughly means what you think: complex oriented and weakly even periodic. I will review this as well. And let's just wonder what happens if we map out this universal deformation ring to any such thing. The key point is that being complex periodic and E-infinity gives rise to a formal group all by itself over E. So there is, the notation is G, E, hat, Q. This is the Quillen formal group. This you get just for any complex periodic E-infinity ring. A basic observation of Quillen that it's even over there. The ecohomology of CP infinity affords some formal group over the coefficients, and the first observation is that E isn't just a homotopy commutative something, but really an E-infinity ring. This formal group is really a formal group over the E-infinity ring. That doesn't even make sense yet because I haven't defined it, but that's what's going to happen. It's a formal group over this E-infinity ring, and at this point, of course, we have two formal groups over the same E-infinity ring, namely the one coming intrinsically from homotopy theory. This is no additional datum, it's just the ring spectrum E gives rise to that formal group. And on the other hand, of course, there is there's of course also universal deformation now in the setting of spectral algebraic geometry. I call this G universal. This is a p-divisible group over this connective E-infinity ring, and you can extract an identity component from it. And ask that it be the Quillen formal group. So you can just ask for maps out of this ring to anything complex periodic, such that the base change of the universal deformation becomes the Quillen formal group. Well, and of course you ask this to happen in a universal way, otherwise you just map to the zero ring. But this is then called the oriented deformation ring. So this is very naturally a moduli problem in spectral algebraic geometry. It gets solved, and then it's proved that it satisfies the properties announced in theorem 008. And this demandment here that the base change be the Quillen formal group, this is also fairly familiar. This is just the same as being an oriented. This is what orientations are about. And this is what accounts for the notation. So this is the oriented deformation ring. The universal example of a deformation of G naught to some complex periodic ring such that the Quillen formal group of this complex periodic ring becomes the deformation. Okay. There can't be any questions because there have been no statements, because everything was undefined. But here's an example. The easiest special case you could contemplate is if you take the p-divisible group to be mu p infinity over fp, and this already gives something very instructive and interesting. So I will say more concretely what this diagram becomes in that special case. So we start with fp, and then the classical deformation, this is Cartier dual to an étale p-divisible group. Whatever that means, it immediately tells you that all the deformation theory is completely trivial. Of course, you believe that the deformation theory is compatible with Cartier duality, and then étale p-divisible groups don't deform. That means the classical deformation ring, you don't have to prove anything, it's just clear. It's the initial p-adically complete ring, which is to say the p-adic integers. And this picture persists to the spectral settings, so the unoriented I rely you tell me when I'm getting too small. I realize something. Okay, you just let me know if the font gets too small. And then this prolongation of the theory from classical rings to connective ring spectra is made in such a way that these things continue to be true. There is Cartier duality, étale things deform trivially in accordance with the general idea that killing off the higher homotopy groups from a connective ring spectrum should be something like a nilpotent thickening. So again, the universal deformation ring of mu p infinity in the spectral setting is the initial E infinity ring, which is p complete, which is to say it's the p complete sphere spectrum. And well, that's pi naught. Okay. Okay. But now how about these orientations? This is where you go to Snaith's theorem. Okay, R oriented G naught is the suspension spectrum of Cp infinity with some Bott element inverted and P completed. This is not visible here from what I've told you so far. Since I didn't say anything what an orientation actually is, there is no way to guess it. But once I will have told you, it will be obvious that this is the oriented deformation ring here. And this is known to be classically by work of Snaith to be p-complete complex K theory. And that, I mean, this, even in this easiest example, you see the two key things you also have to prove in general. So what's non-trivial here? So one statement is this is a pi naught iso. That's a bit hard to believe because, I mean, inverting the Bott element shifts over the homotopy groups all over the place. It's a degree 2 element. But so this is part of the theorem. And what is also claimed here is that this localization has homotopy concentrated in even degrees, pi star even. And that's also a bit hard to believe because in terms of its homotopy, Cp infinity is just as complicated as the sphere itself. And then you shift it all over the place and it gets regular. Fantastic. And in fact, these two features are the key things which happen in general, as you will see by looking at theorem 603 in the paper. And this is beyond the scope of my presentation, but this is where you can look. Everything comes down to proving that this always happens. The map from the unoriented to the oriented deformation ring has these two properties, and the rest is less hard to prove. And so let me point out that even for this also in particular gives a new proof of Snaith's theorem, which is of course a little more roundabout than the original one, but not as much as you may think once you follow the following reference. Akil Matthew has written up a modular proof of just these two facts for Snaith's theorem. So that means there you find a proof of the key theorem of Jacobs, this 603, in the most special case where the p-divisible group is just this one. But this of course has the advantage of separating some things apart. You don't have to learn anything about p-divisible groups. It's just mu p infinity. You can work with this, and you see the modular proof of Snaith's theorem in the easiest possible special case, and that's called method. So this is Akil's note. That's called Snaith's construction of complex K theory. And he attributes this to Hopkins. The proof of the special case of this theorem 603 in this case of leading to Snaith's theorem is attributed to Hopkins. Akhil wrote it up, and it's not linked on his homepage, but last time I checked, Google found it, so good luck. So let me see. Okay, so now I can start filling in some of the technicalities which for the most part concern just this extension, extending these notions from classical commutative algebra to connective ring spectra. And I will start this with formal groups. Here's a definition which is not recommended, but I will have to give it just because I feel obliged to write down anything formally correct and complete. But the somewhat surprising thing is that the technical account of formal groups in the derived in the spectral setting is more cumbersome than the one of p-divisible groups, which is probably quite the contrary of what people feel classically. And now I sell you as a definition something which is in fact a mixture between definitions and characterizations and so forth. But let me first put it and then discuss it. So assume R is the connective E-infinity ring, then you can say a formal group over R is a functor G hat. So the hat is just there to remind us of formal group from connective R algebras to connective set modules. Such that the underlying space valued functor is co-represented by something which looks like a formal power series ring. This is what you would expect classically. I mean, a formal group is a functor valued in abelian groups and representable by the adic spectrum of a power series ring, probably in one variable if you think about one-dimensional formal groups, but the general treatment is no more complicated. So I give the general definition. So such that if you compose with loops infinity, then this is equivalent to the formal spectrum of some adic ring A for an adic R algebra R. Such that, and now I basically want to say, okay, A is a power series ring in a couple of variables over R, but this turns out to be really more complicated in the spectral setting than it is in the classical one. So let me just write down something which is correct and then discuss it further. So I demand that the homotopy of A be isomorphic to a product over symmetric powers of some module M, just base extended to the coefficients of R. This is supposed to be true as a graded pi star R algebra with M a finitely generated projective pi naught R module. Which generates an ideal of definition. I mean, it's an adic ring, so I have to give a ring and an adic topology on its pi naught, and I say M is required to be to generate an ideal of definition, which generates an ideal of definition.
What an adic ring is?
No.
But in the infinity context, what is it there?
Oh, the adic thing is just on the pi naught. So pi naught has to have an adic topology. So this is no more than that.
So what do you mean by the omega infinity? Are you thinking of the Z modules?
Let me just
Okay.
finish writing, otherwise I get more confused than necessary, which generates an ideal of definition. Yeah, the omega here is, I just put it on the blackboard for everyone, loops infinity from connective Z modules to spaces. Oh, spaces.
So you're thinking of Z modules as HC modules?
Oh. I'm not thinking about any models. I mean, so this is. I mean, if you press me here, then I would just always say, that is loops infinity. It's just the right adjoint to the suspension of this infinity categories, and we can discuss this at length, but it's not gonna do any good.
Yeah, it's HZ modules. I mean, it's not discrete Z modules.
No.
Right.
Okay, why not? Okay, in here there is the category of discrete Z modules, and that is equivalent to abelian groups. This may actually come up in a few minutes when talking about p-divisible groups. So it's good to have that on the blackboard. Yeah, so the subtlety is really that you have many more power series rings than you're used to. I mean, if you are of a commutative ring, and let's put apart the fact that we're looking at finitely generated projective modules as just opposed to finite free modules, which would really make this a power series ring in the number of variables given by the rank of the module. But this is very understandable why you want this, because you want a notion which is Zariski local. And even in the classical setting, you can have formal groups which are represented by adic rings, which are not power series rings, but rather something like this, generated by a line bundle and not a free module of rank 1. But otherwise, there's real subtlety here, because I'm unaware of a classification of such adic rings, and you can very easily see this. I mean, the toy case. How would you even write down what a power series ring is in spectral algebraic geometry? Certainly, you have some idea of what the polynomial ring might be. You just take the suspension spectrum of the natural numbers that has pi naught equivalent to a polynomial ring, and now you want to say you complete this. So this is a connective E infinity ring over the sphere, which on its pi naught lifts this polynomial ring. Okay, take this, and now you can complete that. For example, with respect to t, or with respect to t minus 1, and whatever comes to your mind, you can put anything, at least any integer here, t minus something, and already these two choices are inequivalent E infinity rings, and they remain so until you base change them to the integers. So that happens over the sphere, and you can always base change to the integers. Here, of course, if you base change them down to the integers, they will become equivalent as commutative rings, because there's an automorphism which sends 0 to 1, but this is not an automorphism of this E infinity ring. So this is not an argument to seeing that these completions are equivalent adic rings. And in fact, unless I'm mistaken, they are not even equivalent in the very last but one step you can take here. This is in keeping with this idea that the sphere spectrum is a nilpotent thickening of the integers. Over the integers, any one-dimensional formal groups, any two, have the same underlying formal spectrum, just a power series ring in one variable. But as you climb up the sphere, there are many more, and I don't know how many. Anyway, this is sort of an excuse why this definition looks a little roundabout, but I can also turn that into an advertisement. The actual technical treatment Jacob gives is much more beautiful and much more recommended. You go over the dual notion. You don't look at this adic algebras, but you look at the dual co-commutative co-algebras, and then this is probably a little less, honestly, a little less used to this, but it's technically much more convenient. For example, it immediately shows that as you vary R here, okay, I can introduce one piece of notation, I guess. So I call this the infinity category of formal groups over R. And of course, if you do that consequently, the first thing you could ask is, what properties does this functor have? Mapping R to the category of formal groups over R. And if you go to the dual point of view, which in the classical case was actually done by Dieudonné in the 70s, and if you do that here, then it's quite obvious that this is a flat stack, which is really not obvious if you work with adic rings, because these adic topologies mix very badly with the flat topology. Okay, that was tried to be an advertisement that this definition is really bad. It's correct, it's complete, but it's really a mixture of what should be the definition with the characterization. And you put differently, if you take this as your starting definition, you're not going to prove anything. But anyway, it's the correct definition. And now here are some examples. That's not actually an example. That is, I remind you what the spectral algebraic group GM is. That's a pre-example, that's so to speak an algebraic group, which will give rise to both a p-divisible group and a formal group, so it's good to have that around anyways. And this is just defined to be the functor co-represented by the suspension spectrum of the integers, which is fairly natural if you have ever seen GM as an algebraic group. It's co-represented by the ring of Taylor polynomials. But this, of course, only describes a space-valued functor on connective E-infinity rings R. I have to tell you somehow why this should be a connective HZ module rather than a random space. And there are better ways of doing it, but the shortest one I'm aware of is just to claim that this is equivalent to the connective cover of the mapping spectrum over the sphere from the integers into the units of R. And at least this is evidently a connective set module. But it's definitely a result that these are equivalent. And just leave that as it is. So this is the spectral group GM. And from this you can extract a formal group, which is the example properly speaking, by saying that its space of R-valued points is just the fiber of GMR to GMR reduced, where this is a new piece of notation, R reduced for a connective E-infinity ring this is by definition the map to its pi naught R. So this is the idea, you kill all the higher homotopy groups, you map to the pi naught, and then you divide out by the near radical of this classical commutative ring pi naught R. So this is the idea that the general connective E-infinity ring R comes from a reduced one, a classical reduced commutative ring, by first filling in the nilpotent elements into the classical ring, and then filling in the higher nilpotents, the higher homotopy groups, Postnikov, Tauer kind thing, to get R. So okay, this is a formal group.
What are you modding out by? I just missed that part. So the
I write it again. Nil radical, meaning the one of the classical commutative ring pi naught of R. So as written, it's clearly a functor from connective E-infinity rings to connective set modules if you buy part 0. And then it's very easy to see that this is co-represented by the one you had before, and you complete it along the ideal t minus 1, which makes no sense. But after saying that you choose the isomorphism of pi naught sigma infinity integers with this Laurent series ring. This is not called Laurent series, I'm sorry. anyway, t minus 1, which sends 1 in the integers to the variable t. Just to be very specific, I mean, so. But as I said, there is some content here, because if you took just t instead, you would get a different E infinity ring. But of course, here you complete along the 0 section of the algebraic group, so there's nothing you could go, no point where you could go wrong. Now I want to say what complex periodic means for an infinity ring. I used that in the introduction. An infinity ring is complex orientable This is exactly the classical notion. You look at the unit map into this ring, you think of it as sigma infinity minus 2 of CP1, which affords then a canonical map to to sigma infinity minus 2 CP infinity. And an E infinity ring is complex orientable if there exists a map of spectra to make that commutative. And it's called weakly 2 periodic. If sigma 2 of R, thought of as an R module, is locally free of rank 1, which is a very, very nice thing to think about if you ever thought about Picard groups of E infinity rings or something. But it's also equivalent to the completely classical statement that the multiplication map induces an isomorphism from pi minus 2 of R tensored over pi naught of R with pi 2 of R to pi 0. So that is weakly even periodic. And then complex periodic is both R an E infinity ring is complex periodic if it satisfies A and B. So I'd rather wipe the blackboard than do some more exercises.
Niko, so locally free in which topology?
Yeah.
Or what does locally free mean?
Well, in order not to discuss this, I put the second thing here. Of course, since it's a quasi-coherent thing, I mean, this is equivalently in the Étal, flat, Zariski, that's all the same. It's the same condition. So then the remark goes on and says, if R is complex periodic, now comes this story about lifting Quillen's fundamental observation on the homotopy being a formal group to the more structured setting of E infinity rings, assuming that R is an E infinity ring to start with. then you can introduce this Quillen formal group over R to just be the formal spectrum of A equal the R cohomology of Cp infinity. That is unsatisfactory as an explanation, but I can say a few words. So if you now try to check the definition I gave of formal group, then you see the fact that it's co-represented by some adic ring of a suitable form. This is really Quillen's computation of just the complex-oriented cohomology of Cp infinity. It's a formal power series ring, so that is certainly true. But what is unsatisfactory that I'm not telling you, and I will not, why this is a connective set module rather than just some space. Why the functor co-represented by this adic E infinity ring, and we know it's an adic E infinity ring from Quillen's classical work, how this lifts to formal groups. It's not hard to say, it's just beyond the scope of this account. Rather than I will explain the properties I briefly alluded to previously. So what do we need to know about this Quillen formal group? So there's 4321, which characterizes this by a mapping property. So that's of course always a very definite thing. We just characterize, and if you just ask what formal group is that over R, I just describe the functor of points, and that pins it down. So this is definitely an answer. So the statement is that maps of formal groups from the Quillen formal group to any other one is functorially equivalent to maps of pointed spaces from the two-sphere into the underlying space of whatever formal group you're trying to map into. So G hat evaluated on the connective cover of R. So this is a connective Z module spectrum, and then as discussed before, you take the underlying space. And this space, by definition, this is just called the space of pre-orientations of the formal group G hat. This is definitely not the hard part of this. This is not hard, but proving it requires setting up these different point of view on formal groups through co-algebras, which I didn't. So I cannot give you a complete formal proof, but of course you can sense why this is true. Cp infinity being a KC2 means it's the connective set module freely generated by the two-sphere. And then you just take some faith and believe that the function spectrum will be the formal group freely generated by S2. And that's what it says here. Okay. Now, even with less details, there's important construction. I mean, in principle, this characterizes the Quillen formal group by spelling out its mapping property. There is a unique formal group over R which has this property. Okay, that's the Quillen formal group, but there's more to say to it, and we will need this, namely from any, so fix a pre-orientation E of any formal group over a complex periodic ring, then there is a construction of a Bott map. Now things get really sketchy. This Bott map goes from omega G hat, it's called beta E, beta for Bott, and E to remind us that it depends on this pre-orientation, into sigma minus 2 of R. This is a map of line bundles over R. Of course, this secretly claims that the canonical bundle of this formal Lie group you are all familiar with also lifts to spectral algebraic geometry. But there is something to say here. It's not so automatic that this notion of formal group, which I presented, always comes, if it's one-dimensional, I guess well, okay, let's just stick to the one-dimensional case, comes with an canonical invertible R module. And this fellow here is an invertible R module by our assumption that we're weakly even periodic. And there is a map between these. And it has the property that beta E is an isomorphism if and only if the map classified by this pre-orientation is. So this is the map classified by E. As in the first theorem, this pre-orientation is the same as to give a map, and with any pre-orientation comes a map of line bundles, and that is an isomorphism if and only if this map of formal groups is 1. And just to drop the name, this of course then one says that E is an orientation. This is roughly paraphrasing the content of theorem 4.3.23. And the brief takeaway here is that there is a very strong characterization of this Quillen formal group. There is a certain class of E-infinity ring, complex periodic E-infinity rings, which always come automatically equipped with some spectral one-dimensional formal group. And this is characterized uniquely by having this mapping property and being the unique example up to isomorphism of an oriented formal group over this ring spectrum. That just comes for free. This is of course important to remember if you remember this outline of proof, which has gone. Then we're trying to make contact between this purely formal deforming things in the spectral context and taking into account more homotopy theoretic information. We know that whenever we have an complex periodic ring, there is a canonical formal group, and we're trying to put that into relation with the formal group we get from the deformation. So this makes it important to know that this Quillen formal group is pinned down very uniquely by its properties. Okay, thank you very much.
Questions?
Niko, did you suddenly pass from connective rings to non-connective rings in your?
Not suddenly, but that's I have no standing assumption everything is connective. That's true.
Right, but I mean then, according to your definition, the Quillen formal group isn't a formal group, right?
Oh, okay, that is true. I overlooked this. Sorry. So. So for a general, that is true, this makes no sense. But things are set up in such a way that formal groups over an arbitrary infinity ring are the same as over the connected cover. And yeah.
So this story up here where you have the construction of T at K theory, so if you chose like a different type 1 formal group law over FP, like some Galois twist, what can you see like a Snaith type construction for those, or how it's related to the Snaith splitting for T at K theory?
I don't know what Snaith splitting is. Oh, I know what it is. You just ask if I, rather than mu p infinity, I take a Galois twist of that. Yeah. There is not a super large supply of those, but there are some. And of course, the deformation theory can't change at all. It's still étal. And then I guess also, I mean, that also means the orientation. I mean, everything is the same. The bot element is going to change, I guess.
If you were to take a height 2 formal group, does that universal connective spectrum have a name that maybe we knew from before? The thing that the p-adic sphere is, at type 1. I don't know what connective spectrum would go.
Oh, I have no idea.
Height 2.
No, I have no idea. I mean, it's a delocalization of Lubin-Tate theory. So I don't know what that is.
All right. Niko, can you tell us what spoof A means here, or do we need to dualize in order to know what it means?
No, you can say what that means, but this is. I mean, this is always just Okay, if you know what spec means. But that is, of course, easy. I mean, this is just the co-represented functor by that. And then this is always the summand of those maps, of the summand consisting of those points which are represented by ring maps, which on pi naught send an ideal of definition to something nilpotent. So this is fairly elegant in this setup. It's really just, it's an open embedding.
All right, I think lunch is outside, Mr. Kirby. Let's thank Niko again.